Thank you for this opportunity to present my work. I would like also thank the Institute for their warm welcome. And I will speak about some new models, stochastic models in epidemiology, where the infectivity and susceptibility are not a step function as usual, but are some more general random curves. My presentation is based on two works. The first one with Arthur Charpentier from Université of Québec at Montréal, and Félix Poutel-Rodier, now CNRS researcher at Paris Cité. And the second work is with Brice Zotza, who is a PhD student at Aix-Marseille University under the supervision of Raphaël Faurien and Étienne Pardue. So here is my plan. I will first introduce some vocabulary in epidemiology. I'm pretty sure that you already know this vocabulary since the COVID crisis, but I prefer to set the definition at the beginning. Then I will introduce a classical model, the SIRS model, which is quite close to the one I will introduce right after. So after this classical model, I will introduce three models with varying infectivity and susceptibility. In a second part, I will present the main results on the long-term behavior of the disease in these three models. And in the third and fourth part, I will focus on the model with the memory of the past infections. And at last, so I will describe it more clearly. And at last, I will conclude by giving some open questions. So we'll consider an homogeneous population, which means that the individuals all behave in the same way to the disease. So there is no contact matrices, no edge effect, nothing. And we speak of epidemic when a large number of individuals in the population is infected with the disease in a short period of time. A value of interest is R0. This is the average number of infections produced by an infected individual in the population completely vulnerable to the disease. So larger R0, the larger R0, more the disease is dangerous. I don't know how to say that. And we will speak about endemicity when the disease remains present in the population at a relatively low and constant rate in the long time. And now I introduce the infectivity curve, also called the infectious curve, and the susceptibility curve. So the infectivity curve lambda, after being infected, a person will spread the disease at some rate, lambda, during a period of time, Ti. And this infection force of the individual, the infected individual, will depend on the time since its last infection. So it depends on its age, A, which is the duration since the last infection. as I consider a homogeneous population, lambda will be a random curve with the same distribution for all individuals in the population. And now the susceptibility is a probability. So it takes its value between 0 and 1. And it is a probability that an individual will become infected after a contact with an infectious individual. And in this presentation, we will also assume that the susceptibility is not constant in time, and it depends on the age of the individual since the last infection. So as for the lambda curves, gamma is a random curve with the same distribution for all individuals in the population. So we will consider a population of size n. We assume that initially some individuals are infected and the others are vulnerable to the disease, which means that their susceptibility is strictly positive. And I will denote by lambda I of t the infectiousness of the individual I at time t, and gamma I of t its susceptibility at time t. Usually, we classify the individual in the population in 3 categories. The first one, I is the category of the infectious individuals. S is for susceptible, so the category of susceptible individuals, and R the recovered individuals. But this characterization is not well adapted to our models with varying infectivity and susceptibility. And during this talk, I will always assume that the product lambda I, gamma I is equal to 0 for all individuals. What does it mean? It means that if an individual is infected, so lambda I is positive, right? Then its susceptibility is equal to 0, so it cannot be reinfected. So a classical model, the SIRS model. In this model, the individuals jumps from a class to another one. For example, first is one individual is susceptible, and at some random times he becomes infected. Oops. Ah, yes. Okay. So at this time, it becomes infected. So its susceptibility jumps from 1 to 0. During a period of time ti, which is usually modeled by with an exponential random variable, the individual is infectious. And after this period, this duration, it becomes recovered. So the infectiousness jumps from the constant value beta to 0. It stays recovered during some period, exponential period TR. And after this period, the susceptibility jumps from 0 to 1, and so on. So this model is a Markovian model, and the reproduction number R0 in this model is equal to beta over nu. And And what we can see, the value is not comes from somewhere. Indeed, we can see that this value is indeed the expectation of the mean value of the infectiousness lambda over the edges. If I compute this expectation here, it is just the expectation of beta times Ti. And for an exponential random variable, the expectation of Ti is just 1 over mu. Do you have something to? Ah, yes. But there is no reason to imagine that the infectiousness will jump from 0 to some constant value at each infection. And there is no reason to think that this infectiousness stay constant during the infectious duration. We can imagine that we don't have the same infectiousness right after the infection or 3 days later. And for the susceptibility, there is no reason to think that it will jump from 0 to 1 after a recovery time. So that is why Forien, Pang, Pardue, and Brice-Zodsa has introduced this model with varying infectivity and susceptibility. So I forget to mention that I will speak a lot of their work. So in their model, the susceptibility is some random curve, increasing random curve, and the infectiousness is another random curve. The assumptions are the following. So at each infectious time, a new curve of infectiousness lambda and a new curve of susceptibility gamma are sampled. They assume that lambda is a bonding function with compact support. And also, so the susceptibility is between 0 and 1. The product gamma lambda is equal to 0 almost surely. And for the existence of endemicity, that gamma is a non-decreasing function. And the value of interest is still defined in the same way. This is the first model. The second model is the one we have introduced with Félix Poutel-Rodier and Arthur Charpentier. We have added a vaccination policy. So we have random curves of susceptibility and infectivity. And at each event, oh, I forgot something before. So here the curves are sampled at each new infection. So the edge will be the time since the last infection. The definition will be different in this model. We will sample a new infectivity curve lambda or new susceptibility curve sigma. It's not the same notation. After each new event, which can be an infection, a vaccination, or a recovery. And the vaccination policy we have introduced, it's just a renewal process between two infections. We have also assumed that lambda is a bounded function with compact support. Sigma is non-decreasing, but in this case, when there is an infection here, I will sample a new value of sigma, and I will introduce a vaccination policy. So this is a renewal time. So I introduce some independent vaccination duration, independent random variable, which represents the duration between two vaccination time. At each vaccination, after each vaccination, I resample a new susceptibility curve. So here I have sigma 1, sigma 2, maybe sigma 0 here, sigma 1 here, sigma 3, so on until the new infection time. So I1, I2. And at the new infection time, the susceptibility jumps from its positive value to 0, and I sample infectivity curve lambda. So the function defined, the function gamma defined in the first model was a function, the function of susceptibility defined in the first model was a function between two infections time, and it was assumed that it was an increasing function. And here, if I collect off all of these sigma functions, we can see that gamma is no more a non-decreasing function. First model, second model. We have also assumed that the vaccination policy is independent of the infectivity and the susceptibility. The vaccination policy is a health policy, and the curves lambda and sigma depend on the disease.
If vaccination happens during a infective period, what do you think the supplement?
If a vaccination, oops.
Yeah.
No, in our model, we will sample a vaccination time after a recovery. So we can't have a vaccination when we are infected. So we have also assumed that the distribution of sigma is the same after a vaccination or an infection, that lambda and sigma are independent, which was not the case in the first model. And there is no memory, as in the first model, of the previous infection. And now the last model with memory. So we still have random curves of infectivity and susceptibility. We are considering here a parametric model, which means that the curves of lambda and gamma belong to some set, probability set of curves. So they will depend on a parameter theta which belongs to this probability space. And at each new infection, we will sample a new parameter theta through some memory kernel K, which depends on the value of the parameter right before the infection. So the curves will jump from their value with parameter theta to the value with the parameter theta tilde. We also assume that lambda is a bounding function. Gamma is also between 0 and 1 with a product with lambda equal to 0. But we don't have monotone condition on the susceptibility. And in this case, the value of interest R0 can be written in the following way because we have a parametric model. So the main question we are interested in, but there are many other questions. Is there an endemic equilibrium? And how can we characterize it? And is there convergence of the disease to the disease-free, either the disease-free equilibrium or the endemic equilibrium? Under which conditions? In this talk, I will focus on the first question, and if I have some time, I will speak about the second question, but it is a quite difficult question, even in the classical models. So here are the main results. In their paper article, Forien, Pang, Pardo, and Zotsa prove that when the limit of gamma when A goes to plus infinity is well defined, and if the susceptibility is non-decreasing, when the reproduction number is bigger than this quantity, this expectation, the expectation of 1 over gamma star, where gamma star is the limit here, there exists an endemic equilibrium. Maybe there is not only one, but at least one. With the paper, in the paper with Félix Coutel-Rodier and Arthur Charpentier, we prove that the existence of an endemic equilibrium when R0 is bigger than the expectation of the duration between two vaccination times over the mean value of the susceptibility between two vaccination times. So if R0 is bigger than this quantity, there exists an endemic equilibrium. And in the last, okay. Yes, we have proved also that this condition is necessary for some particular cases of sigma. We think that it is true in general, but it's just a conjecture. And for the last model, the result is not nice. We have proved that if this limit exists, so in the first model, it was under the conditions that the limit when the edge goes to plus infinity of the susceptibility exists. In the third model, the condition is on the mean value one over b, the integral between 0 and b of gamma of A exists. there is an endemic equilibrium if this condition is satisfied. I will write it. So this condition is not really nice. So gamma star is the limit here. And sigma star is indeed the a normalized eigenfunction related to the eigenvalue 1 of this linear operator. And we now renormalize this eigenfunction such as this integral is equal to 1. Yes.
Sigma star is unique.
Sigma star is unique, yes, due to this normalization. It exists and is unique. So now I will focus on the third model. So we consider a population of size n with an initial proportion of individuals who are infectious. Each individuals are described by two random processes. The edge, so AI of t is the edge of the individual I at time t. It means that it is the duration since the last infection, and theta I of t is the threat of the individual at time t, so the value of its parameter. With those two quantities, I can compute the infectiousness of the individual I at time t. It's just the value of lambda at edge AI with parameter theta I, and its susceptibility, which is defined in the same way. So as I said, the classification as SIR is not well adapted for regular functions. So we will work with the empirical measure of edges and threats. And I introduce the global force, the global infection force of the disease, which is the mean value of the susceptibility over the population. So if I consider an individual I, he will be infected at time t at rate gamma I times the global force of infection. So if gamma I is equal to 0, it cannot be infected. So this is the case when the individual is already infected or when is totally immune to the disease. And if the individual is infected at time t, its edge will jump to 0. A new threat is sampled according to the memory kernel, K, which depends on the value of the threat right before the infection. And we can see that we can write the evolution of the edges and threats as the solution of a system of stochastic differential equations where Qi here are independent Poisson measure. So the edge will grow linearly until an infection. And the trait stay constant between two infections. So we can easily observe that this system is indeed a system of piecewise deterministic Markov processes. Okay, so we are interested in the long-time behavior of the disease. but it's not easy to work with this kind of system. So we will consider a large population. So we will take the limit when the size of the population goes to infinity and study the deterministic limit of this model. In the classical case of SIRS model, the limit is characterized by this system of ordinary differential equations. So S is the density of susceptible individuals in the population, I, the density of infected individuals, and R, the density of recovered individuals. And we have this dichotomy when R0 defined as beta over mu. When R0 is bigger than 1, there is a stable endemic equilibrium. And when R0 is smaller than 1, the disease disappears in a long time. In our model, it's quite more complicated, but indeed, Florian, Pang, Pardo, and Zosa made all the jobs for us. So adapting the result, we can prove that there is propagation of chaos. It means that this empirical measure will converge to the distribution, the weak solution of this equation, where R is the jump term, the edge jumps from the value A to 0, and theta jumps from the value, the parameter jumps from the value theta to theta tilde, according to the kernel, the memory kernel. So the propagation of chaos, what does it mean? It means that when the size of the, we imagine that initially the individuals are identically and independently distributed. At each time, oh, I forgot to say that, sorry. At each time, we can see that the individuals are in interaction through this global force of infection, which depends on all the individuals. But when the size of the population goes to infinity, if I consider a fixed group of individuals, when the size goes to infinity, these individuals will behave like independent individuals with the same distribution, and the common distribution, their common distribution is the weak solution of this equation. So here we have a nonlinear coefficient. So the bracket here is the usual notation for the integral with respect to some measure of mu. So this is the integral of lambda with respect to mu. And if we assume that initially the distribution has a density, at each time mu t has also a density denoted by ut, and this density is solution of this partial differential equations. So in the case of the SIRS model, we had a system of ordinary differential equation. Here we have partial differential equations. It comes from the fact that the system is Markovian in edge. If I don't consider the edge, the system is not Markovian. So we can prove that this system represents the disease and threats of typical individuals. As I said, we have PDs and not ODs. And we have proved that there is existence and uniqueness of the solution of a such system. So here's the first of infection of the disease in a large population. So I'm interested in the equilibrium state. We are in an equilibrium state when the density doesn't depend on T and the force of infection doesn't depend on T. So we have two possible equilibria. A disease-free equilibrium when the force of infection is equal to 0. And an endemic equilibrium when the force of infection is strictly positive, which means that the disease remains active in long time. So I won't give the proof of this result, but it is we have used spectral theory for operators, and we have proved that when this mean value converges when b goes to infinity to some function gamma star plus some technical assumption, there exists an endemic equilibrium under this condition, where sigma star is uniquely defined by those two conditions, two equations. I can make a remark. Maybe if I introduce, so P is a distribution, is a probability distribution on the parameters, but if I make a change of measure and I introduce P star, this new probability distribution on the set of parameters, this condition can be written in the following way. So we have 1 over gamma star. Indeed, this integral, if I divide by the L1 norm of sigma star, is just the expectation under the distribution, the probability measure P star of 1 over gamma star, and R0 star is the expectation of the mean value of the susceptibility over edges. And donc, we can rewrite this condition under this form. And this is the same as in the first model where there was no memory. It is just that we have changed the measure due to the memory of the model. So it was not nice, but indeed, it's quite similar to what Forien, Pang, Pardue, and Zotzer have shown. So now I will make some link with the other models. So the first model, there was no memory of the previous infection. So we can take the kernel memory doesn't depend on its previous value of the parameter. So we can take k equal to 1. And the function sigma star is in this case, so k is equal to 1 should be equal to the integral of sigma star with respect to the measure P. This means that sigma star is a constant. And the second conditions means that the integral of lambda theta sigma star dA P d theta should be equal to 1. But if sigma star is a constant, I can put it before the integral. And what we can see is that sigma star is equal to 1 over the integral of lambda dA d theta, which is equal to 1 over the expectation of the integral of lambda over the edges which was the definition of the reproduction number in the first model. So here is what I have said. And in their paper, they have assumed that gamma, the susceptibility is non-decreasing. In this case, the limit of 1 over b is integral between 0 and b of gamma is indeed the limit of the function gamma when it is non-decreasing. So this exists and it is equal to gamma star, the limit of gamma. And we recover the result. And we don't need this assumption of monotony on the susceptibility. In the second model with a vaccination policy, so there is still no memory of the previous infection. So sigma star is always constant, equal to this value, 1 over R0. And we will compute the value of the limit gamma star in this configuration. So let tau the successive time of vaccination. Indeed, the first time is the duration of the infected, how can I say that? Of the infectiousness. And the next TVK are the duration between two vaccine shots. And the susceptibility can be written in as the following compound sum, where capital N is the counting process of the renewal process, and sigma N are IDs non-decreasing curves. So this is the function gamma defined here. And using the classical renewal theory, we can easily prove that, so if I consider this integral, I can decompose it between two vaccination time. The first term, so 1 over b, I decompose it as nb over b times 1 over nb. The first term converges to 1 over the expectation duration of between two vaccination time. The second one converges to this expectation, and the last term converges to 0. So in this case, this integral converges to this value of gamma star. It's not written here, but it was the threshold introduced in the paper with Arthur Charpentier and Félix Coutel-Rodier. So we recover this result. And indeed, we don't need also this assumption. We don't need sigma to be monotone to obtain this result. So in conclusion, in this talk, we have introduced different stochastic models with varying infectivity and susceptibility. I hope I was not too fast. I've presented some links between them, obtain a large law of number for those models. This is the propagation of chaos. We have obtained an endemicity criterion for the deterministic limit. In the work with Arthur Charpentier and Félix Coutel-Rodier, at each change of state, which means infection, recovery, or vaccination, new curves are sampled independently according to the same distribution for the whole distribution, for the whole population. The susceptibility is assumed non-decreasing between two events, independent of the infectiousness, and a vaccination policy was studied. And in the work in progress with Brice Zotzer, at each new infection, new curves of infectivity and susceptibility are sampled with memory of the last infection. There is no monotone condition. We can have dependence between the value of the susceptibility and the infectiousness. But this is a parametric model. So we have some criterion to characterize. We know that when R0 is big enough, we will have an endemic equilibrium. But is there convergence to this equilibrium? We don't know. In their paper, Forien, Pang, Pardo, and Zotzer prove that without monotone condition on the susceptibility, that when R0 is small enough, there is convergence to the disease-free equilibrium. In our work with Brice Zotzer, we have proved under this condition, which is a quite strong condition, but we have proved something. When R0 is large enough, we have a local stability of the endemic equilibrium. It means that when the distribution of the age and threats start from a distribution close to the equilibrium, then we will converge to this equilibrium. And some open questions. This condition is really strong because A star doesn't depend on theta. It is the same for all the value of the parameters. So I cannot, for example, take the susceptibility in the SIRS model, which is indeed just the indicator function of A bigger than some exponential random variable, because an exponential random variable is not bounded, so it doesn't work. So we would like to have a better condition to have this local stability. I forgot to say that it was proved in the case without memory, so the kernel memory is equal to 1. Can we have something when we take into account the memory? It seems really difficult. And other open question concerns heterogeneous population. That's it. Yes. You have a way to see, if I can compute the value. Yes, in some cases, I can compute sigma star explicitly, even when there is a memory of the previous parameter. So we can do it in some cases. I mean, it's complicated. You want us to check this condition? Let me think. Sigma star is an eigenfunction of some linear operator. So I'm not an expert in that, but maybe there are some techniques. I don't know.
think I was going to ask, it's all about this picture. So this is sort of illustrating the convergence when we start from microscopic.
Yes. In red, it is the distribution, it is the deterministic curves. This is the fraction of infected individuals in the population. So in the large population, when n goes to infinity, and the yes.
You started with like just a small infected population, which you expect. Sort of metastasis.
The disease can always disappear, even if when R0 is large enough, it can always disappear. So what we have proved is that we have local stability. So if we start from a population quite close to the equilibrium, we will converge to the equilibrium. But if not, I don't know. I think we won't have a global stability. Indeed, in a population of fixed size n, there is a positive probability that the disease disappears. When the size goes to plus infinity, I don't really know. I think there is a probability to touch 0, but don't know. It's really difficult.
In practice, if we take COVID or anything, what is the shape of this infection curve?
They are as what I draw.
So you have like a
yes, it is smooth. Yes, it is.
Next question.